Good morning. This is the first laboratory demonstration for ECE 441, the automatic controls class. You're looking right now at the mechanical system that we will be using throughout the semester, but for laboratory number 1, what we're going to concentrate on is actually identifying the system transfer function associated with this mechanical system. You can see, I hope, in the video that we have a way of adjusting the different number of masses on the system. Each mass is what we're going to assume is 500 grams. We have multiple springs that you will be able to go ahead and use the screwdriver, probably just the tip, and adjust the spring. If you are not using spring number 4, if you've been assigned a different spring, you'll want to unscrew the spring that's already in the system and replace it with the spring that you've been assigned. That will then also need to be your masses, however many you're assigned to put in. You'll need to thumb that down tight, and then this is the dash pot that you will want to be measuring in terms of the B coefficient subsequent in the design or in the lab. Here is where the force will be applied through this rack and pinion mechanism, and what we want to do now is go through the equations that will tell us what's actually going to happen in our system. But before we get there, you might just note that there is a scale on this mass. We will be commanding the mass to go roughly from the 0 mark here over a little beyond 1 centimeter. 1 centimeter in this system corresponds to 1,600 counts roughly, and we are going to command the system to go 2,000 counts, come back and hold that for about 3 seconds, go back to 2,000, etc., and we'll repeat that process 3 times. That's where we're going. The position of this mass is actually measured by this encoder, and that information will then be relayed to us via the computer, and we'll be able to then visually inspect the step response and also get that in MATLAB so that we can analyze the data in MATLAB. We'll now move over to the board and go through the derivation of how we can take this measured system data and compute the spring constant K, the damping rate factor B, and the hardware gain in our system between the input and the force that's applied to that particular system. We're now over at the whiteboard, and I have sketched our schematic of the mass spring dash pot system. Here is our applied force that hopefully you remember from the motor that's coming in through the motor. We also have this gain, gamma, that is parameterized with 2 parameters, K sub PF, which we will actually put in place in our software. K hardware is what we need to then evaluate or measure or identify. This is then our system. Here is our position x and the corresponding velocity x dot. In lab 1, we will be using gamma, which is parameterized in this way, K hardware times K sub PF. Our goal is to find the spring constant, the dash pot gain B, and the hardware gain in our system, K hardware, remembering that gamma is that product of K hardware and K sub PF. If you go through the dynamic equations of motion, you should be able to derive this relationship between the mass, the spring, and the dash pot. This is a block diagram depiction of the same system. Here is our applied input, U. This is our position Laplace transform, X. We will be applying a step input, U of S, equal to A over S, where in this particular system we will be using our position units as counts, and we will be commanding when we do apply a step for the system to move to 2,000 counts. And as I said earlier, the 1 centimeter in our system is roughly 1,600 counts. We're going a little bit more than 1 centimeter when we apply a step command of A, amplitude of 2,000 counts. Relating this to what we've done in class, we've been modeling a second order transfer function, g of s, as some alpha over s plus sigma squared plus omega sub d squared. That is what? Written in the form of here's our real part, here's our imaginary part, and this is related to the gain in our system. You can also write that in terms of this standard complex pole representation in terms of zeta, the damping ratio, and our natural frequency omega sub n. That's our system transfer function g of s. When we scale that or apply an input a over s, we obtain the Laplace transform of the position of our system, which is then alpha a over the quantity, or this product of the s term coming from our step and the complex pole factor, s squared plus 2 zeta omega sub ns plus omega sub n squared. What I've done now is I've erased part of the board and rewritten x of s, our expression for the Laplace transform of the position variable, rewrote that just as we had on the previous side of the board. That's alpha a over s times the quantity s plus sigma squared plus omega sub d squared. We can write that consistent with our standard zeta omega sub n representation of the complex pole factor by factoring out this gain variable alpha a over omega sub n squared. You can also think of what? The partial fraction expansion of this particular expression. We have the constant term a1 over s. We have a cosine factor, an exponentially decaying cosine factor weighted by b1. And likewise, we have the partial fraction expansion term associated with the exponentially decaying sine wave. Written in this way, we can immediately think of our position signal, x of t, of the mass being made up of a constant plus a damped, exponentially damped cosine with the gain b1 and an exponentially decaying sine with the gain c1. We can also write that as what we did in class, which was to say that's some magnitude a1 times this standard inverse Laplace transform of this particular expression, which was in table 2.3 of the textbook. This then inverse Laplace transforms into this representation where beta is this square root of 1 minus sigma squared over in our S domain plot. That's related to the angle theta, or that's the zeta value is related to theta. And this is our damping, sigma, and this is our imaginary part, omega sub d, with the radial distance being our natural frequency associated with that complex pole. What we want to do now then is use this information to determine from the transient response or from the step response what these different values are, and in particular, what is our damping, sigma, what is our damped frequency, omega sub d, and what is our alpha term in our original transfer function, g of s. We're looking for alpha, sigma, and omega sub d, and then we can define our transfer function, g of s, and we'll be able to then relate that to the spring constant, the damping constant B, and the hardware gain K hardware. I've now sketched the trajectory that you will measure over with the physical system. This is our position information or position data. We have our peak of the response, we have the time that it takes to peak, and we have our settled value or the steady state value, which we've been denoting as A sub 1. We want to now find these parameters, our damped frequency, our damping, and our gain value that are in our transfer function g of s from these parameters that we measure physically in the response trajectory. We can find our damped frequency, omega sub d, from our peak time, or time to peak, realizing from what we've derived in class that the peak time is actually pi over omega sub d. Omega sub d then is simply solved for, and we find that the damped frequency, omega sub d, is pi over time to peak. We now have that one of our three quantities. We want to now find a second of our three quantities, which is the sigma value. We want to use the peak value in our response, the final value, a sub 1, to find zeta, our damping ratio, or our damping sigma, after we've already found omega sub d. We can determine experimentally what our percent overshoot is for this particular system by taking the peak, subtracting from that the final value, dividing all of that by the final value, and multiplying by 100. That gives us our percent overshoot, which might be 20%, it might be 80%. We plug that 80 or 20 in here for PO in the two locations, and using this formula, which is the natural log of that ratio squared divided by pi squared plus that ratio squared again, or natural log of that ratio squared again, we also want to make sure and take the square root of that. That gives us our damping ratio zeta. Once we have zeta, if we want sigma, we can find it because we know this relationship between our damped frequency, omega sub d, and our natural frequency, omega sub n. This we can then solve for our natural frequency. Once we have our natural frequency, we can scale that or multiply that by our damping ratio zeta to obtain our sigma value, which is the real part of our complex pole pair, which is sigma is equal to zeta omega sub n, or it's this ratio of zeta and the square root of 1 minus zeta squared times our damped frequency, omega sub d. We now have two of our three unknowns. We now know sigma, we now know omega sub d, and we will now try to find our last unknown, which is the alpha, based on our final value of this particular response, a sub 1. Remember our trajectory response of the position of the mass with respect to time as we commanded it to move 2,000 counts. It will settle at some value a sub 1. That might be 1,400, it may be 2,400 counts. We want to measure that value, a1, or our final value of the position information, and we will use that by means of the final value theorem, which you've learned through Laplace transforms, to determine a relationship between a sub 1, the final value that we measure, and the alpha, which is the unknown gain value in our transfer function g of s. The final value theorem says that this a1, or the x final value of our position, is equal to the limit as s goes to 0 of s times x of s. X of s, remember, is the system g of s scaled by the step command u of s. Here is g of s, there is u of s. We're multiplying it by s, which is convenient. That s cancels that s, and we now let s go to 0 in the remaining terms, and we end up with a1 equaling alpha times a, capital A, over sigma squared plus omega sub d squared. Remembering our relationship between the real part and the imaginary part of our complex roots says that sigma squared plus omega sub d squared is actually equal to the hypotenuse, or the radial distance away from the origin that pole is, and that's our natural frequency squared, meaning the final value of our position is related to the alpha in our transfer function by alpha a over omega sub n squared. We already know omega sub n from the previous two steps in our derivation. We know a, that's how much we've commanded the system to move. That was 2,000. The only unknown in this expression is alpha, and we can solve for alpha. That will be a1, which might be 1,400, it may be 2100 times our natural frequency squared divided by 2000, or A. Remembering omega sub n squared is also sigma squared plus omega sub d squared. We now know alpha, we know sigma, and we know omega sub d. We now want to go back to our original system model, which was in terms of the spring constant K, the damping factor B, and the hardware gain K sub hardware, and use alpha, sigma, and omega sub d to determine the spring constant, the damping constant, and our hardware gain. We have already derived alpha, sigma, and omega sub d in our transfer function from the measured data. What we want to do now is assume that we have our given mass, and the mass, the total mass of our system, and I'll refer to that at the very end, is related to how many individual masses we have. Each of those individual masses is 1/2 of a kilogram. The carriage itself is 1/2 of a kilogram, and you will then have to figure out what your total mass is that you were given. Whether you're given 1 mass, 2 masses, or 4 masses, you'll then be able to calculate your total mass. If we know that the gamma, the gain factor, is a combination of K sub PF and K hardware, K sub PF you will assign in your software, we will then be able to find K hardware from this gamma value in our G of S transfer function. This is the transfer function that we started with from our physical modeling of the mass spring damper system. We equate that to the transfer function from, let's say, class. This then we can expand or square this S plus sigma factor, and we end up with the following transfer function, and we can now just simply equate coefficients to determine our spring constant K, our damping constant B, and our gain in the system gamma. For example, if we compare the constant term in the denominator, we see that K over M is actually equal to omega sub n squared, or sigma squared plus omega sub d squared. We make that equality, K over M, and if you know what your mass is, you now know your spring constant. That's just your total mass of the system, which might be 2 kilograms, it might be 2.5 kilograms, it might be 1 kilogram, is that mass in kilograms times the natural frequency, which you've just determined earlier from your measured data. That's now your spring constant. Your spring constant might be 400 newtons per meter, it might be 800 newtons per meter, somewhere around you should end up in the hundreds for your spring constant. B over M, likewise, the linear factor in this transfer function is then equal to 2 sigma. You can now use that relationship to scale 2 sigma by your mass M to end up with your damping coefficient B. That's 2m times sigma. Finally, we can equate numerator coefficients. Gamma over M is equal to alpha. Gamma over M, which, as we said in this first lab, is K hardware times K sub PF. K sub PF you will assign in your own lab. That might be 0.075, it might be 0.75. You need to figure out what K sub PF is that works in your system. For that particular value, you know you have a given mass value. You've just calculated alpha. You can now solve for your K hardware, and that might be in the thousands. B might be in the single digits to in the tens or 20 region. And now you have your spring constant K, your damping factor B, and your hardware gain K sub PF. Just to keep in mind what you have, the carriage itself is 1/2 of a kilogram, which means if you do not have any masses attached to your carriage, your total mass of the system would be 0.5 kilograms. If you have one mass, then the total mass M in this formulation would be 1/2 plus 1/2, which gives us a total of 1 for M. Likewise, in terms of relating these counts to a physical distance, we see that there's 1,604.1 counts every centimeter of distance that you have in your physical system. That information, together with the position step response, should allow you to identify your spring constant, your damping ratio, or I'm sorry, your damping factor coefficient B, and your hardware gain K sub hardware. We're now sitting in front of the computer, which is connected to the ECP, or Educational Control Products rectilinear plant mechanism, through a box that you download your commands to and settings to, and it then puts that out to the hardware. What you will want to do once you are here at the computer workstation is actually log in, and that's like you normally log in to your ECE Win domain. And hopefully I can remember my password and that wasn't captured in the video. And now we have the screen that you will see, hopefully, something similar to that. Hopefully you will have this ECP32 icon on your desktop, and you will then want to double click on that. And as that's coming up, you can also then go over and push the on button on the Educational Control Products hardware box, and it is just to the right of the PC that is in the controls lab, and that should then get you ready for executing the commands that you need to execute for lab number 1. The first thing that you'll want to do is actually prepare ECP, or the software, for lab number 1. You'll go to the file, load settings, and under the C drive, the local disk drive, you will see a folder entitled ECE 441. In there you will see the configuration file for lab number 1, and it's entitled ECE 441 _ lab1.cfg. Open that, and by opening that, it's now stored the appropriate commands internal to the software package, and hopefully that will allow most of the settings to already be predefined and you won't have to run through that many settings. If you look at the screen, you will see that you are running the software on the linear inertia model, model 210. Then you have several different screen images that you can see. One is the commanded position. We're now at 0 counts. The control effort is expressed in voltage. We really won't be using that in this particular lab, but it's interesting to see how much voltage is being applied to the system in order to make it move to 2000 counts. We then will see movement on the encoder 1 position. Right now it's at 9 counts, and we really want to be starting at 0, and to zero that out you'll want to go up to utility and say 0 position, and now we are zeroed out in terms of our counts. You can then watch that encoder position or the following error, that's just the negative essentially, and see how much your following error is relative to the commanded position. We will then be inputting a command of 2000, and you'll be hopefully getting close to that, but maybe not, and we'll use that information to derive our model. We now want to go and start up the control algorithm. You then go to Setup, click on Setup Control Algorithm. The button should be highlighted that says State Feedback. You'll want to click on the wrench, which is the setup algorithm. Inside here you should see the K sub PF window, and all of the gains should actually be 0. The gains that we will be concerned with are K sub 1 and K2, which are the position gain and the velocity gain for mass number 1 associated with encoder 1 positional information. K sub PF, we will, right now it's set nominally to be 0.15. That may or may not be a good value depending on what spring you are using. Right now I have it configured with spring number 4, and I believe I have 2 masses on the carriage. That actually this particular case of PF may not work for that combination, but I want to actually demonstrate that in this lab and show what you need to do to accommodate that. So if it's too big, you can come up or return to this location and reduce that to maybe 0.75 and save it. Let me go back to what it defaulted to be, which was 0.15, and I'll say that's okay. Now I need to actually download that to the ECP box by clicking on the Implement Algorithm. That now closes the loop. It really is not feeding anything back because all of our gains were 0 except for the forward gain of case of PF, which is now at 0.15. In preparation for exciting the system with a step input, go to the command line and click on the trajectory, and you will see different kinds of trajectories available to you. Make sure the button next to step is pushed. You can look at the setup. We want to command the system to go to 2,000 counts, dwell there for 3,000 milliseconds or 3 seconds, and repeat that process for 3 different repetitions. And this should be in the closed loop step configuration. That's okay. Now what we want to do is make sure that everything is zeroed out, and we have already done that via the utility. We now want to execute that command by clicking on Command Execute. The normal data sampling is fine, and click on Run and hope that everything is okay in terms of your case of PF gain. You can hear and you can actually see that we have actually hit the limit, and the limit switch is presently broken, or it would have aborted the system. If you hear that happening, which it's hitting the stop, you can go ahead and cancel. Aborting control really won't do anything because there's no control really applied to the system. There's no feedback gains. We've now canceled that, and what we want to do is go back to Setup, Control Algorithm, go into Setup Algorithm, and reduce this case of PF gain to, let's say, half of what it was. Let's now apply 0.075. Click on OK. Now we need to implement that algorithm. That's been done. Now we can go back. The trajectory hasn't changed. We want to execute the same. Our counts are still at 0. Let's go ahead and run. And you can be following this encoder, and you can see that it is reaching a steady state, but it's about 300 counts less than what it maybe is commanded to be, but that's okay. We can make those adjustments in Lab 2 and Lab 3 to zero out those following errors. It will now upload that data into the control box or into the computer so that we are now able to examine what we just captured with the plotting line, and then we do setup plot. It's already pre-set up for us if we now use the appropriate lab file that we loaded in to begin with. We're plotting commanded position in the encoder 1 position, and we want to then just say plot data. The green is then the actual position information, and you can see it does overshoot, it comes back under, and then it goes to a final value. We will then be able to examine this trajectory and find the peak value, the time that it peaked relative to when the command actually started. So if we found the peak here, it would actually be the physical value that we measure. If we looked at this peak, then we would want to make sure that if it was peaking at 6.1, we would want to subtract the 6 so that we have a peak time of 0.1, and we can also find this steady state value that we've settled at. That's our A sub 1 in the program. In order to do that, we can do it in MATLAB. We need to go to the data line, do export raw data, and save this into your particular location that you can find or that you have access to that you can then run MATLAB on. And I will go ahead and save that in a particular location that I might want to save it in. For example, This is actually Lab 1, 2 masses are M2 and Spring 4, and I would then click Save and it would save it for me in that particular manner. Now what we can do, now that we have it saved, is we can go to my computer and find that file. And once we've found that file, what we need to do is actually modify it slightly so that MATLAB can actually work with it. If you see what we have now on the screen, we have some text on the top line and an open square bracket. We need to actually eliminate all of those. You can highlight those and delete those and maybe insert a space in order to line things up. This gives us column data. This is then the sample number. This is the time that happened. This is the position that was commanded to go to 2,000 counts. This was the physical position of encoder 1 that is measured. And those are the columns of interest to us in terms of keeping track of this data. If we now go to the end of the file, which you can do by hitting Control End in Notepad, then I want to remove that closing square bracket and replace it with a semicolon. Now I can save this file, and you can save it as what you just had it defined as, or you could say, well, this is really modified, or it's the MATLAB file. I will just say M and save, and now this is in a form without the comments that MATLAB will be able to read in, and we can then analyze that data in MATLAB. For example, if we go to the MATLAB or open MATLAB, once MATLAB is open, we will try to locate that file, we will try to load it in and plot some of the information and show how you can then find the peak value. You can then find the time that it peaks, and you can also find the steady state value. I'm now changing directories so that I can gain access to the file that I've already saved. And now the file that I just saved, I can introduce that into MATLAB by the load command, load, and now I'll type the name that's MATLAB compatible. It was Lab 1, Mass 2, Spring 4, modified.txt. And now instead of retyping Lab 1, M2, S4, M, I'm just going to relabel that as data, or assign a variable data to that matrix of columns of data. And now I have access to what? The time, which is, or was, the second column in data. I also have the reference command, which I believe was the third column in data, and the position data, which was the fourth column. And I'm pulling off those appropriate columns by doing the wildcard symbol in MATLAB, which is the colon, saying give me all the rows in the second column, third column, and fourth column. And now I can actually plot the position command maybe as a solid line and the reference command as a dotted line in MATLAB. Hopefully I've used the correct columns for those particular pieces of data. And this should be very consistent with what you just saw in the ECP software. You can now find the peak value and the time that it peaks either by doing a max, or you can say turn on the zoom on the graphics window. And you can go back to the window and zoom in on the appropriate peak value as much as you want, and you could then record that peak, which looks like it's 2,758 counts at 6.198, which remember you need to take that 6 off of there, so it's peaking at 0.198, and now you can hit the right mouse and say reset to the original view. You can now zoom in on the final value, and you now see that it's at 1,750 counts. Again, you can go back to the original, and now you have your 3 data points that you need from MATLAB to essentially complete the lab.